Hello once again, AP Calc BC students. Mr. Recker here from Avon High School, and literally, little change of venue here for the videos. We are at Avon High School, but it's an empty classroom here. I'll let you guys take a look here. It's kind of empty, but this is where all the magic happens. Yeah, maybe so. So we're going to take a look at our final example. This is example 8 in my sort of fictitious topic 8.14. It's fictitious in that there is no topic 8.14 in the course and exam description as published by the College Board for Calc BC. But this is a topic that it's certainly important enough to study if you have the time to do so, because it's very prominently taught in a Calculus 2 class at the college level. But once again, as I've said many times in these videos, work is not something that will be tested on the BC exam. Can't promise, though, what's going to happen on your Calc 2 exams. We're probably going to see it in college. So we're going to talk about work required to empty a conical tank of water. And, you know, it is kind of funny because you think, how many conical tanks of water have you ever seen in your life? And one of the ones that comes to my mind is the old paper cup that you might see at the doctor's office or the dentist's office. And I've often wondered, who made up the idea to make those cups in the shape of a cone? Yeah, that's interesting, isn't it? All right, let's go to our problem over here. It says we've got this conical tank that has a top diameter of 10 feet and a height of 15 feet as shown in that figure to the right. We're going to fill that with water. It's all the way to the top, and that water is going to weigh 62.4 pounds per cubic foot. And then a pump is going to take the water from the bottom of the tank, and it's going to take it to a level 6 feet above the tank. So in this problem, we're going to place the origin at the bottom, and we're going to label important points. So I'm going to do that for you. And then we're going to ask how much work is done in emptying the entire tank. Now, I've got this problem scaffolded a little bit. So, normally, let's say in a textbook problem, you might see, no part A, part B, part C, and then boom, you're just going to go right to the final piece here where you're going to write and evaluate the integral that represents the work. So we'll go back to the beginning and we'll scaffold this and make this sort of progress so that it is a little bit easier to understand. So it says if the water level happens to be at the point XY, and so at some point we know that that is definitely going to happen, right? The water is in the tank and it's going to be pumped upward. We know that at this phase of the game it's going to have a height here that's going to always be depicted by the value of y. So we're asking what is the distance that slice of water needs to go to be pumped to the top of the tank. And so what we're going to do here is kind of think about this representative slice of water like this. Now, as I said before, the distance that particular layer of water is from the bottom or vertex of the cone is definitely going to be y. The height of the cone itself we know is 15, as indicated in the problem. But remember, we've got this extra 6 here. I'm just going to rewrite it so that it's consistent, right, in red there. And so we have this overall height of 15 from the very bottom of the picture to the top of the picture. And so innately what that is going to suggest is that this layer of water will have to travel that distance. Now, I know that it seems a little bit confusing here because of the way that this structure is drawn on paper. We're not going to pay a lot of attention to like the work that's going to have to take place for the water to get over here and for all of this traveling and so forth. Let's kind of focus on this as our main diagram and this layer of water wanting to get all the way to the top of the picture. And so what that is suggesting is that we're going to have a distance of 21 minus y going on. All right? So next up, what is the volume and the weight of that slice of water? Well, the volume and the weight, if you remember, are two very important pieces that are going to help us determine the force. And remember that work has always been force times distance. But now we're seeing a new representation of force that is very often taking the sort of the form of the volume times the density. And the density in this problem is very often going to be equated to the idea of the weight, all right? How much this water weighs per cubic foot. Because as I said before, in this problem, volume is going to be measured in cubic feet. Density is pounds per cubic feet. Once those cubic feet cancel, you're left with pounds, and that is a very reasonable label or unit for our force. And so we've got to figure out what is the volume of this slice of water. And that slice of water, if I kind of redraw it here, is nothing more than a very tiny disc or a cylinder. And we know that the volume of any standard cylinder is pi r squared h. Well, in this particular problem, the h is very easily taken care of, as it's just the change in y. It's just the thickness that we have going on with this little disc of water. The r is the part that's going to be very, very challenging, okay? Because the r, in and of itself right now, is nothing more than just a radius that takes on the variable x. Now, if you look at our picture, that's certainly the case. The distance that we would have from this center line, the y-axis, to the outside edge of the cone, no matter where we are, right, down in our disk, or anywhere else for that matter, is always going to be a measure of x. So preliminarily, that's a good word, isn't it? We could say that the volume is pi x squared delta y. And there's nothing wrong with that at the outset. And then, of course, the weight of that slice of water we know is going to be the 62. Let me kind of rephrase that. The density is going to be 62.4 pounds per cubic foot. But then when we factor in the volume as well, then we could say the weight, which I don't like that word weight, so I'm going to replace it with the word force, right? And that force is just going to be volume times density. And so we're going to go ahead and put the 62.4 in as a factor and multiply it by the pi x squared. And then we've got delta y. You could think of it as dy. Eventually it's going to transform into a dy when we have our integral put together. Okay, now you guys, we have a big problem here. It says you may see that we have two variables in our weight, x and y, and we'll need to change everything so that the variables are only going to be y. All right, and the reason why is we're setting up our integral with respect to y. We always have with these water problems because we're moving our water a vertical distance. Okay, and then one more time, I want to reiterate that this picture is not meant for you to kind of like look at and say that, oh, this is the path that the water is traveling. We could have our suction tube actually going right through the cone and making sure that it stays consistent with the top of the water level, and so that it's siphoning the water there at the top. All right, so we are physically moving it this distance. All right, so how are we going to fix our little problem? Well, it turns out there are two different things that you can do. One might be very reminiscent of some things that you did in solving some previous problems, maybe some of the related rate problems that you may have solved from Calculus AB or Calculus 1. And so what I'm going to do is look into this picture and notice something. I have a triangle right here. Yes, I do. That is a triangle that would be consistent with the amount of water at any moment. So if I extract that triangle, I know that this triangle is always going to have a radius of x and a height of y. Now, when I say radius of a triangle, that sounds kind of silly. So we're going to use that more so as a horizontal section or a base. The base is x rather than the radius. Triangles don't have a radii. Now we go back to the picture and we look at another triangle that would encompass the entire shape. Keep in mind what the radius and the height were, right? The diameter was 10, so the radius would be 5, and the height was still 15. So if I extract this triangle, take him down all the way to here, once again, as we have indicated, this distance is 5. Remember, the diameter was 10, and this distance is 15. And what you have are a pair of what kind of triangles? You're right, similar triangles. And that allows us to set up any variety of proportions. There's quite a few that you could toss together. I'll use this relationship. And so now we're able to solve this for our x, because this is going to get our expression to be in terms of the y that we want. So x is going to be y divided by 3. So that would be that relationship that we want. Now, there is another way to do this if you prefer, and a lot of times students will have to use this particular method because the similar triangles relationship just isn't quite there. But you could use an ordered pair value of 515 and an ordered pair value of 0, 0, and you could construct the equation of that line, right? Just using your normal point slope formula, etc. And you could then solve that line for x in terms of y. That's going to be really important for other problems that don't lend themselves very well to a cone or triangles. Perfect case is in my particular set of homework problems, Skill Builder. One of the last problems, or the last problem, is to find the amount of work it takes to drink a strawberry milkshake, given its particular density and whatnot. And so as you can see in this problem, we don't have the luxury of subdividing this into what would be similar triangles. But you could very easily use ordered pairs here along the edges to find an equation so that you get a relationship for this varying radius, this varying x value that's going to come about as the slice of milkshake obviously changes its height as it's being sucked out of the cup. All right, come back to our problem here. Honestly, we are really close now to finishing this up. We are at part D, which will put this one all to rest. So the amount of work that we're going to do is always going to be a force times a distance. So if you remember, our force from up here in part B is now going to have this 62.4 pi times x squared, where the x has now been deemed to be y over 3. I'm going to hold off on my delta y for just a moment because I want to get my distance in here, and the distance is what we computed way back here in part A. All right, so let me come up down here so I can kind of get in on the action and watch this. So we got 21 minus y, and now we're going to close this off with our dy, which is part of our incremental force now, instead of our incremental distance, right? It was involved in our force. And then, of course, we have to integrate this, and we want to empty the entire tank. Remember, this tank was full to the top, so it had this much water in it when we started this whole process. And so you would just simply take a look at the boundaries, and they would start down here at 0 and end up here at 15. It's very important that you don't think that the boundaries go from 0 to 21, because there is no water up there beyond 15, right? 21 is the kind of the extra 6 feet of empty space that water's still going to have to travel, but there was no water there to begin with. This is not a very difficult antiderivative to take. You probably have to square the y over 3, distribute it into the 21 minus y, and then you're just basically taking the antiderivative of a polynomial. So that's not too bad. If you also type it into your graphing calculator, you should be able to come up with an answer. And I'd like to invite you guys to go ahead and do that just to verify that the answer is 238,918. Let's go ahead and use AP Calculus rules of rounding, even though this is not going to appear on an AP Calculus exam. So we have our 0.121. And because our units are in feet and pounds, our work unit will be foot-pounds. And there we have it. This water has officially been pumped through that valve, and so it's now going to be leaving this conical tank and going up 6 feet above it. Anyway, I hope that helps. This is the last of our work problems that we're going to discuss here in our video series. You have several problems that I have in my skill builder that those of you that are Avon High School students are hopefully working on. And of course, I can provide a link to that particular assignment in the description of the video if anyone wants to take a look. Anyway, I hope this helps, and we'll see you next time.